All right, another video. Make sure I'm on mute here. Am I on mute? I hope so. Yes. So another video. I am reading pages, I believe, 86 through 91. No, through 90 of Machine Learning by Tom and Mitchell. And this was relatively, I guess, not difficult, but a lot of things to understand. So, they explain what a perceptron is. It's basically a neural network's version of a neuron. It's a single unit that takes a vector of real valued inputs and basically outputs a binary, not binary, one of two outputs, either one or negative one. It's a linear calculation. And you have, similar to our checkers example, in which you had each attribute and then you had a weight associated with that attribute, and it was the sum of all of them. That's what a perceptron does. So 1 would be true, -1 would be 0, or -1 would be a negative example, +1 would be a positive example. So there's that. That's a perceptron. And then they go into the representational power of perceptrons. So if you imagine it, and they go into what's called a hyperplane decision surface in n-dimensional spaces of instances, in an n-dimensional space of instances. So imagine you have oranges and apples in a pool. What you would like to do, your goal is to separate the apples and oranges by just taking a board or a long plank, let's say like a door, right? You're going to throw the door into the pool. Ideally, you would like to position that door so that you have apples and oranges in the pool. All the apples are on one side of the door and all the oranges are on the other side of the door, which is essentially what you're trying to do in a machine learning algorithm. Is you're trying to get your algorithm, your program, to classify things correctly. So that's what they mean by a hyperplane decision surface. The door is the hyperplane, and hyperplane is basically a plane in dimensions that the human eye cannot see. So a plane, which would be a thin door with the zero depth, is a it's a lot. No, it's a plane. Yeah, it's a plane. Anything above that would be a hyperplane. So there's that. It goes into what perceptrons can represent. So they can represent and or functions. They can also represent not and functions. So for example, a not and function would be that the output is false only if both inputs are true. They can represent not or functions. Output is true only if both inputs are false. However, they cannot express X or exclusive or functions. Output is true only if inputs are different. And essentially that's like, if you look on a Cartesian plane and you were to have a a positive example in quadrant 1 and a positive example in quadrant 4. You have a negative example in quadrant 2 and a negative example in quadrant 3. There's no way to draw a line to separate the negatives from the positives. And that's essentially what it's saying. At least in a perceptron cannot represent that. So there's that. And then they go into the perceptron training rule. Ooh, I'm running out of time here. So the perceptron training rule versus the gradient descent and delta rule, they're both ways of reducing the error, right? Updating the weights. The difference between the two is that sorry. Why is this only going? Oh, because I'm on the wrong thing here. The difference between the two. So you have. Oh, I gotta find it. So the perceptron rule only updates weights only when a mistake is made. The gradient descent updates the weights continuously to minimize the error. So it doesn't matter if it comes across a mistake or not. The perceptron rule works only if the data is linearly separable. We talked about that. Gradient descent can handle it if it's non-linearly separable. Output of the perceptron rule is binary, 0 or 1. Gradient descent, it can be continuous. And there's one other difference that I won't go into. Thanks for watching the video. I don't know if it helped you, but it helped me, and I'll see you in the next one. See ya.